So please, James Cole, come forward with your talk on optimal heating time for water extraction from icy lunar simulants using low power microwave heating. Please go for it.
Thank you. Can you hear me? Am I visible as well?
Yes.
Okay, cool. Okay. So yeah, my name is James Cole and I'm a second year PhD student at the Open University in the UK. Today I'm going to be presenting the work from my project thus far. I would like to thank the Open University's SRA and the STFC for funding my project. So my project is, of course, in the domain of in-situ resource utilisation. Setting up ISRU facilities on the lunar surface will provide a key step in setting up a circular cislunar economy, which will allow us to move infrastructure off the Earth's surface and allow strong economic gains. One of the most enticing resources is the ice in the lunar poles in the permanently shallow regions. These regions can reach as low as 30 Kelvin, meaning this water should be stable over geological timescales. Remote sensing has indicated these regions could hold up to 38% of water. However, LCROSS has taken the only in-situ measurement, which was about 6 weight percent. Current estimates indicate there could be gigatons of ice either in the surface, the subsurface, or even lower. It should be mentioned that the current knowledge of the form of ice is not very well understood and will be a key measurement taken the next few years with CLIPS landers, etc. So I'm aiming to explore using microwave heating as an extraction technique for removing this water ice. So why microwaves? So unlike other heating techniques, microwaves heat up the material volumetrically. So unlike heating techniques such as solar beams or laser sintering, volumetric heating removes the dependency on the thermal conductivity. And the thermal conductivity of lunar regolith is very low. And this is why with solar and laser, you can only heat a shallow layer before you need to remove it. It's been found in previous work that microwaves couple efficiently to lunar simulants, and they should couple even more efficiently to lunar regolith with the additional nanophase ion, which can't be replicated terrestrially, well, not easily anyway. And of course, microwave heating can additionally be used to sinter or melt the material at high temperatures to create infrastructure or other materials. Using microwaves, however, is a bit of a balancing act. So the equation on the top basically just shows you the volumetric heating, and it's proportional to the frequency of the electromagnetic waves you use. So you might naturally ask, why not simply increase the frequency and get more powerful heating? That is answered by the bottom equation, which shows the skin depth, which essentially shows how far the microwaves can penetrate into a material. This is inversely proportional to the frequency. So if you increase the frequency, you get more powerful heating, but only to a shallower depth. And this doesn't even come into talking about the complexity of material properties that change with both frequency and temperature. So there's a lot of refinements when you're using microwave heating. At the Open University, we have a bespoke microwave heating unit, or an MHU, that produces 2.45 gigahertz microwaves between 250 and 1,000 watts. The microwaves are emitted into a 110 millimeter cavity that can be, the tuning arm can be lowered or raised to change the height of the cavity, so therefore you can move the hotspot for the microwaves. The cavity can be pumped down to a pressure of 1 millibar for the work I've been doing. We can go much lower, however, with the amount of water vapor that I produce, it's much safer to stay at 1 millibar. It should be mentioned that the current setup is not capable of capturing the water, but is something we are working on. So I made some basic icy simulants for these experiments using the so-called mud pie technique. These samples are not indicative of what lunar ice will be like. However, they are easy to make, or relatively easy to make, and can be easily reproducible. So you desiccate the simulant at 250 degrees for 24 hours. Then you add deionized water to make either 5 or 10 weight percent samples, which was then allowed to settle in an airtight container for 12 hours, at least 12 hours, to diffuse the water through the sample. We then place the samples in a cryogenic cooler for at least 90 minutes or until the sample had reached less than 120 Kelvin. The simulants used for all these experiments was either LHS1 or OPRH3M, which are Highland simulants, or OPRL2NT, which is a high titanium mare. This offers us a wide range of possible lunar conditions. A finished sample can be seen in the center image, where it's been placed in a ceramic crucible and wrapped with ceramic paper. So the ceramic paper allows, when we're pumping down the sample, it stops the temperature raising too much, and the crucible essentially just holds the material. Both of these materials should be transparent to microwave, so should not affect the heating profile. So for these experiments, we were interested in the extraction efficiency, which is simply a measure of how much of the initial water content has been lost. This was done in a very simplistic way, so you measure the mass of the sample before and after the heating run. It's very difficult to measure the mass live while the microwaves are operating due to the interference from the microwaves themselves. All of the heating runs were done using 250-watt microwaves. This means we were concentrating on a sort of more Pathfinder mission sort of power regime. The blown up image on the right is a picture of the sample, and what you can see there is the plasmas that form as volatiles are released from the sample. So we conducted some initial experiments to investigate the effect of both simulant choice and water content, both simulant choice and water content on the extraction efficiency. So all of these samples were heated for 30 minutes with 3 repeats done for each weight percentage and simulant variety. So first thing to mention here is that each variety demonstrated quite high water extraction, at least 50%, which is quite good, I think, for only 30 minutes of heating. OPRL2NT demonstrates higher extraction efficiencies than OPRH3N. However, if you look at the water contents for each simulant, you find that OPRH3N demonstrates higher extraction efficiencies for 5 weight percent over 10 weight percent. However, OPRL2NT is the other way around. So these differences could be due to the chemical composition of the simulants, or is it simply due to the way the simulants absorb the water? We're still investigating this. One thing to note here is that in previous work conducted by my supervisor, Sungwoo Lim, who's going to talk after me, he found that Highland simulants couple a lot less efficiently than Mare simulants. However, I feel the extraction efficiencies here are close enough to note that it seems to be the water that plays a large effect on the extraction efficiency, not the simulant choice itself. And one thing to note here is that these experiments used a prototype cryogenic cooler that got the samples down to roughly 120 Kelvin. For the results I'm going to show you on the next slide, we were able to get down to 100 Kelvin, so keep that in mind. So yes, I next investigated the optimum heating time for this heating method by looking at how extraction efficiency changes with different heating times. Each point on this graph, so the blue point, is a different run to a different sample. So that's got to be kept in mind because of the fact we couldn't measure the extraction efficiency live. We had to do it each, had to measure the mass before and after. We had to use a different sample each time. And this graph demonstrates first off that there is a minimum amount of energy that is required before water starts being released. So up until 30 minutes, no water is released at all. After this point, the water very quickly gets released. So I feel at this point we've reached a temperature where either sublimation or vaporization takes over quite quickly. And then you reach a plateau where essentially no more water can be released. You're almost at 100%. So I should mention this is using LHS1 simulant with 5 weight percent water content. Obviously in the future, I will use different simulants and different water contents. With further work, I feel I can demonstrate there is an optimum heating time. So where you can say, this is where we'll get the most extraction efficiency, but at the lowest amount of energy, which I think is a very important thing for future missions. And I theorize that this will obviously occur at different times for different water content and different simulants, and especially different forms of ice. So as I mentioned, the temperature for these samples were lower, so they started off at 100 Kelvin. And this is why, if you look at the 30 to 40 minute mark, the extraction efficiency is a lot lower than what I showed at the previous slide, which were above 50%. Sorry. What this highlights is that the temperature of a sample in terms of microwave heating is very important, especially if you're looking into the efficiency of extracting the water. And therefore, it's very important that we know the temperatures of the regions. If we are going to send microwave heating to the moon, we need to know the temperature of the regions we're sending them to know what extraction efficiency we'd expect from such a region. So looking forward to the rest of my project, I first would like to develop more complex samples. As I mentioned, the mud pie samples I've made thus far aren't conducive of lunar conditions. So I'd like to develop a granular icy simulant or a frosty icy simulant. So that is currently undergoing. I'm working on that as we speak. But this is probably where we'll be limited by the microwave heating unit, as that is at room temperature as you pump down. So if you want to make anything more complex, such as with amorphous ice, you simply can't because it will just heat up too quickly. And then we also have 2 developments planned for the equipment itself to aid in future investigations. So as I mentioned, we measure the mass quite simply at the moment, just before and after the heating run. However, we are developing a prototype of something I'm calling the dynamic mass instrument that solves this problem with the use of a counterbalance. And by using a ceramic arm that goes through a Faraday gap, the microwave should not be able to interfere with the electronics and any of the metal involved, which means we should be able to get live mass measurements of the sample as it's heated. So we should be able to find exactly where the heating is occurring. The water loss is occurring. And then thanks to funding from the UKSA, the vacuum line of the system is being upgraded to allow water to be captured onto a cold trap. This will allow a secondary measurement of the extraction efficiency, which I feel is very important, as this system can be quite difficult to gauge. And then this system will also allow us to take a mass spec reading as the sample's being heated, which again I think will be very useful to see not only is water being developed, but how does that change? Does the water split into oxygen and hydrogen plasmas and things of that nature? So yeah, in summary, obviously this is preliminary work, so I've got a lot more data to take, and so hopefully maybe next year I'll be able to present a lot more concrete data. However, I've already found that the extraction efficiency of this process is very high, and could be made, I think, even higher with certain optimizations of the system. And also that the temperature is key. The temperature of the sample seems to play a big role in what extraction efficiency you can gather. So yeah, I'm going to stop speaking now. So thank you for listening. Has anybody got any questions?
Thanks very much, James. And there is a question. Amrush Mohammed wonder if you consider artificial heat generated by impacts in your experimental paradigm.
No, we haven't really got that far yet in terms of we're still at the process of working out the equipment, how it works. I think any of that sort of stuff would be occurring later down the line. But yeah, the biggest problem is probably getting the temperature that low that you could then start artificially talking about how impact would change the sample.
Thanks.
There's another question by Philip Reis. I can read that if you want to. Yeah. Did you measure or simulate temperature distribution in the sample during heating? And could the differences in extraction efficiency be caused by inhomogeneous water distribution in the sample?
So we haven't altered the temperature yet. We've just been aiming to get as low as possible as we're using a prototype. But that's definitely one thing I'd like to look into is, first off, can we get any lower? Because obviously we want to get more towards the 40 Kelvin, 50 Kelvin region. I don't think we're going to get much lower, to be honest, using terrestrial equipment. But then maybe we can increase use samples at different temperatures and see how that affects it and go from there. What was the second part of the question, sorry?
Could the differences in extraction efficiency be caused by inhomogeneous water distribution in the sample?
It could be. I'm hoping that when we're leaving it overnight that it is distributing evenly. Obviously, it's difficult to check that because we then need to run the sample. We can't just take the samples apart. But it's definitely something we'll look into. And I think it'll be more of an issue when we look into more complicated simulants, so frosty simulants and things like that. That's where the distribution will probably have an effect.
Okay, thank you very much.